And this is another example for describe the body plot. Example 13 and 3 and 4. This is very important example. Here we will discuss about the complex pole. It's quite important. In this example, the transfer network functions or transfer function is given in this manner. We have a kind of the function of omega is a frequency is represented in this manner. Okay, some variable k0 square and j omega square plus j2 zeta omega 0 and omega plus omega 0 square. So here is k and omega 0 and zeta is some constant. This is a function of omega and omega. Actually, this is a function of the j omega. This type, this network functions, this is kind of a second order network functions. We call this is a second order network function. Or transfer function. So this second order, what's the meaning of second order? Because the denominator, the maximum order of the omega is second. So we call this second order the network functions. Here we have three parameters, k and omega 0 and zeta. K is the same thing we discussed before. This is a DC gain. And omega 0 we call it corner frequency. And zeta is we call this a damping ratio. So this is a quite important form. So in this example, we will draw the asymptotic curve when the denominator has a second order the low-pass filters times. Actually, this is kind of a low-pass filter, especially in the second order. So now we will draw the body flat of the second order the low-pass filters. So to make a simple problems, let k is 1, then h omega will be present as j omega square plus j2 zeta omega 0 omega plus omega 0 square and omega 0 square. So this can be represented because j square is -1. So we will present it in this manner. Omega 0 square minus omega square plus j2 zeta omega 0 omega and k omega 0 square. So here we will represent that this h in the butterfly, and first we will discuss about only the magnitude of that. So if you simplify these functions, actually numerator as a very simple, this is constant values in this case, but denominator has the function of the omega. So to draw the butterfly, we need to simplify the the denominator here. Omega 0 square minus omega square plus J2 zeta omega 0 omega can be simply, the important point is omega 0 corner frequency. So omega is smaller than omega 0, then omega 0 square minus omega square plus Je zeta omega 0 omega. Here, this is omega is very small compared to the omega 0. So, and omega is very small compared to the omega 0. So because this is the square, for example, this meaning is that let omega 0 is 100, then omega is 10, that means omega 0 square minus omega square plus J2 zeta omega 0 omega, that is minus 100 plus J2 zeta, that's it. So it's quite long, quite big values, but this is very small compared to here. Why? Because this is square. So we can simplify that, we can ignore because omega 0 square is quite big values. In the same manner, when omega is larger than omega 0, then omega 0 square minus omega square plus J2 zeta omega 0 omega. Here, this is quite big values compared to that, so we can ignore. And this is a big value square, but this is a big values just to first order, so we can ignore. So then the result will be minus omega square. So in this point of that, then h omega was omega 0 square and omega 0 square minus omega square plus Je zeta omega 0 omega. Then it will be when omega is smaller than omega 0, then that will be, because of that, this is a omega 0 square, there is 1. When omega is larger than omega 0, then that will be minus omega 0, minus omega 0 square, omega 0 square. So minus omega square, omega 0 square. So to draw the butterfly here, so what should we do? We should represent this magnitude of h is the division, and the dB 20 log h will be 20 log 1 when omega is more than omega 0, so there will be 0 dB. So in the case of here is 20 log minus omega square omega 0 square. So because this is a magnitude of that, so we ignore that here. So that will be 20 log omega 0 square minus 20 log omega square. So here is 40 log omega 0 minus 40 log omega. This is a function of log omega. And important thing is the value is 40. Remember that in the first order case, this is a function of log omega, but that is a 20 in the case of the first order systems. But second order system, this is a 40. That's quite fun. So this is omega is larger than omega 0 corner frequency. Then we need to draw the magnitude of that here. So we draw it here. Here, this is log omega, and here is a 20 log h. The unit of this is dB, and this is corner frequency log omega 0. Then here, the less than omega 0, this area, in this area, the dominant thing is 0 dB. So here we have this is 0 dB. And here, from the larger than omega 0 here, in this area, we have this waveform, this line, this function of omega zeros, and so we can define some value here. This is log 10 omega 0. Then when insert this omega 0 here, then there will be 0 dBs. So when we insert, for example, we insert here 40 log omega 0 minus 40 log 10 omega 0 means 40 log omega 0 minus 40 log 10 minus 40 log omega 0. So it's eliminated. So that will be minus 40. What's the meaning of that? Here we have another values. This is minus 40 dB, and the line is connected in this manner. Here, that is minus 40 dB per 1 decade. So this is, because of this is a second order systems, that is 40. So we call this as low pass filter. Why? When the frequency is smaller than omega zeros, the gain is 0 dB. 0 dB means the magnitude is 1. That means input and output, the magnitude is the same. But the high frequency compared to corner frequency, then the magnitude is decreased, especially with minus 40 dB per decade. That means that value is very small. So when it means minus 20 dB means this is a kind of 1/10. The 40 dB means it is 1/100th. So in high frequency, in this area, the signal is not passing through the circuits, no pass. In this area, all pass. So we call this is a this is a low pass filters. The low frequency, the signal is passing. the high frequency signal is stopped. So this, compared to the first order system, the second order system has a minus 40 dB per decade, the values in this manner. So it's important things. So if we have a third order systems, then that will be here. If third order system, then there's a minus 60 dB for decade. So we know that second order system in the minus 40 dB per decade. So you know that first order system, then there is minus 20 dB for decade. And one more important thing is here. There are one more important thing is here. With asymptotic curve, the actually very important things here. 20 log h at omega is omega zeros. In the asymptotic curve, that value was the 0 dB here. But actually, this is not 0. Why? Because of this is second order systems. You insert it exactly. Use 0 at but in the real value is not. You insert exact values log h when omega 0 is 20 log what is h omega 0 square minus omega 0 square plus 2 zeta omega 0 square omega 0 square. So 20 log, eliminate each others in this manner, 1. So there will be 2 zeta, 1 over 2 zeta at omega is omega zeros. This is not 0 dB. What's the meaning of that? Zeta, when zeta is half, then there will be 0 dBs. So that means we will derive the figures in second order systems generally. Okay, we'll do again here. Actually, this is asymptotic curve here, right? But to rewrite here, the real values at 20 log h at omega is omega 0 is not 1. This is actually the 20 log 1 over 2 zeta. So actually z is 0.5, then that value is 20 log h. Omega is omega 0 was 0 dB, but zeta is 0.05. That means 20 log 10 means 20 dB. So for example, zeta is 0.5, that means here is the point of there. This is a point of the values. In this case, the body flow looks like that. In this manner. Looks like this is a zeta is 0.05. In the case of 0.5, in this case, looks like we go close like that, then the line is looks like that. I mean, it's not, let's say that is not good way for me in this manner. And there is, for example, zeta is 5, then 20 log 0.1 is minus 20 dB. So that means here. So in this case, the flow looks like that. This is zeta is 5. Zeta is 0.5. So the getting zeta is increased. Then body flow is moved from here to there. It's a kind of the function of the zeta. So what's the meaning of the zeta here? You can see that when zeta is 0.05, then what happens? In this case, there is 20 dB. So when the frequency is very low here, here, then the gain is 1. But how about this here? In here, in this point, when the frequency is omega zeros, the gain is 10. What's the meaning of that? So input V in 10, then V out will be 100 at this frequency, especially this frequency. And in here, and there, gain will be minus 40 means 0.01. Then V in 10 and V out will be 0.1. And here V is 10, then V out is 10. So that's the characteristic of the zeta. So the secondary systems, the decay, the ratio is very high because this is a 40-degree decay. But we have the zeta. Because of zeta, at the corner frequency, the gain will be increased in this manner. So this is characteristic of the zeta. Then I will give you another example. 13-5, and find the asymptotic curve. of the body plot, H omega is 5, 1.0.21 J omega and J omega 1 plus J omega over 2, the 1.0.6 J omega over 50 minus 50 omega square. And this one is quite complicated. So before discuss about that, I will summarize how to draw the body plot, especially the magnitude of the body plot. You know, you remember here, in the case of the secondary systems, what happened in the corner frequency over here? In the corner frequency, what happened here? Because at the frequency, it changes. This is I mean, before the frequency of the corner frequency, after corner frequency, we have a minus 40 dB for decade. We have a minus 40 dB per decade. This is fun, interesting, because this is a secondary system. There are at the point of the corner frequency, they have a minus 40 dB per decade in the body plot. So this is very important things. So what happened here? What happened here? In this case, you remember that, okay, I will give you an example. In this case, what happens? This is denominators that we met the omega here. We met omega here. We met omega here, right? Before that, we met the pole. We call this a pole. Before met the pole, that is the slope of that here is, slope of this is, here is 20 dB per decade. But how about after pole? The decade is 0. Why? There are no, this is 0 log omega. Then another example. Okay, here. In this case, we met omega 1 here. In this manner, we met omega 1 here. We met omega 1 here. Before omega 1, that is the slope of that is 0. This is actually the plus 0 log omega here, actually. But after, actually, I'm sorry, this is not here, okay. Actually, we have, actually here is 0 log omega here. But after omega 1, the slope is minus 20 dB per decade. Remember that if frequencies increase, then meet the corner frequency, especially the pole, then the slope reduces minus 20 dB per decade. From the 0 to minus 20, and here is plus 20 to 0. How about the secondary systems? In the secondary systems, here before corner frequency, That is actually 0 plus 0 log omega. The slope is 0 here. This is a slope is 0 dB per decade. But how about after the omega zeros? The slope is minus 40 dB per decade. What's the meaning of that? When the frequency meet the second of the pole, then the slope changes minus 40 dB. That's a rule. We have another example like that here. So I will explain what happens now the frequency at the zero or pole. This is example. We have h is a delta function can be represented in here 1 plus j omega 2 omega 1 plus j omega 3 omega and k 1 plus j omega 1 omega. So we have some assumption that let omega 1 omega 2 omega 3. And here I will explain how to draw the magnitude of the Buddha plot of h. So to do that here, at first we need to define the magnitude of h. First, omega is smaller than omega. We have three frequency ranges here. This is omega. We have omega 1, omega 2, and omega 3. And we need to define the omega, the h, this area, and this area, and this area, and this area. So this is 1, and 2, 3, 4. Here this is the first. Then that will be, you can say that that ones, but because of here we can ignore this is very small, this is very small, very small. So this variable will be k. In second, the omega is placed here, then omega 1 and omega 2. So we have same things, but a little different. So here we have this. Because omega is larger than omega 1, so this is compared to large, compared to the 1. So we can ignore, in this case, this is 0, and this is 0. So in this case, there will be, because of this is magnitude, so k omega 1 and omega. In third, we have omega 2, omega, and omega 3. This is a third, right? So we have the same things like that. Then this is compared to high, larger than here, so we can ignore, because omega is larger than omega 2, so we can ignore. Then, and this is a 0. So that will be k omega 1 and omega 2. This is constant values. And first, omega is omega 4, larger than omega 4. In this area, this is 4 fours. So here, that values. So here, can ignore and ignore and ignore. Why? This is larger than values 1. So that will be k omega 1, omega 2, omega 3, and 1 half omega. So we get it the asymptotic values of h. So what should we do? Then because we draw the body plot and magnitude in dB, so we can make this in here. The first 20 log, we insert that values here. Okay. The second 20 log this in here. So that will be k omega 1 omega. So it will be 20 log k minus 20 log omega 1 and plus 20 log omega. Log here, we have to insert that is here. So that will be k omega 1 omega 2. So that will be 20 log k minus 20 log omega 1 plus 20 log omega 2. This is last thing here. That will be here. K omega 1 omega 2 omega 3 1 half omega. So that will be 20 log k minus 20 log omega 1 plus 20 log omega 2 plus 20 log omega 3 minus 20 log omega. And here, this is a omega is smaller than omega 1. This is a omega placed between omega 1 and omega 2. This is omega 2 and omega 3. Here, omega is larger than omega 3. So this is the magnitude of here. Then we can draw the magnitude in the body plots, because body plot is placed in this manner here. And so we have here, then this is a magnitude, and this is a log omega here. So we have three values: log omega 1, log omega 2, and log omega 3. So in this area, we have constant values. So there is a variable, this is 20 log k. So we can draw in this way here. And next is in this area, 20 log k minus 20 log 1 plus, this is a variable log omega, and the slope is plus 20. So we have a line in this manner here. And here the slope is 20 dB per decade, and that variable will be 20 log k minus 20 log omega 1 and plus 20 log omega 2. And this area we have that variables, so this isn't like that here. And it's the same variables in here. And in this area here, this is constant values, and we have log omega and slope is minus 20. So we have a slope in this manner. So this is minus 20 dB per decade. So this is the way to draw the body plot. You know, but in here I will tell you about what is the pole and zeros. So we call omega 1 is zeros, and omega 2 and omega 3 is a pole. What happens at 0 and pole? Actually, this is a 0, and this is pole, and this is pole. So at first we have a derivatives like that, but at the zeros, what happens? In here, the slope of that is 0 dB per decade, but at 0, the slope is increase plus 20. And at the pole, slope, this is a 0 dB per decade. That means at pole, the slope is minus 20. But you make the pole against, then slope is also minus 20. So if we meet the 0, the slope is increased 20 degree. In the case of the first other pole, possible 0. In the case this is a first other 0, then slope is plus 20. Then this is a first order at the pole, then slope is minus 20. The same way, this is the first other pole, therefore slope is minus 20. So slope changes. Because of the 0, slope is changed plus 20. Because this is a pole, plus is the slope is changed minus 20. So this is 20 dB, minus 20 dB, 0 dB. We made the pole again. This is the first other pole. So 0 dB change to minus 20 dB per decade. This is a role of the 0 and pole. So therefore, you make a network function in this manner, then you can define very simply what is a pole and what is the zeros. Then you can draw the Boolean plot, very simple. So we can solve this example. We have, in the viewpoint over here, we have the 0. Where is 0? You know that. You can replace this will be 1 plus J10 omega. The same things. So 0 is 10. The unit of the frequency is a radian per sec. And how about pole? We have 2 poles here. Actually, this is a pole, and this is a pole, and this is second of the poles. So first of the pole is 0 and 2 radian per sec. This is 0 and 2. And second of the pole we have This is second of all. This is a 50 radian per sec. So at first we need to define the zero DC gains. But actually, because the omega, I mean, what is DC gains? H omega go to the zeros, but denominator they are the omega. So if we go to the omega zeros, then we cannot define the variables. So in this case, you need to fix some values, which are very small, because this is the zero and pole is a 10, 2, and 50. Then you can define the very small compared to these variables. So to get a DC gains, in this case, a very small, very low frequency gains, H omega was 1 is meant here. Then that is, you insert 1, then they're simple. So you insert the variables here, then (20 log 5), because we insert the 1 here, very small values, then minus 20 log is 1. So it'll be approximately 14 dB. That means that when omega is 1, then the DC gain, the gain is 14. And in the very low frequency, because of these terms, the starting very frequency, the slope is very low frequency. I don't know, to show that, I will give it simply the asymptotic approach here. H is a very small frequency, make a very small zero right in here. Then what happens? That is 5. Then where's that? This is omega and 1 and 1. This is 5 of that one here. So how about, we define, we have 3 frequency more, 2, 10, and 50 here. So what happened here? That therefore 20 log H will be 20 log 5. So 20 log 5 minus 20 log omega. Very small frequency. That means in the start point is omega, log omega. The slope is minus 20 dB. Then we have more frequency. Where is it? And 2 radian per sec and 50 radian per sec, and we have zeros 10 radian per sec. So we can draw. We can draw the something like that. This is the frequency. This is magnitude of here. This is 20 log H, and this is log omega. And we defined, this is, for example, 0.1 radian log 0.1, and this is a log 1, and this is a log 10, this is log 100. Then maybe our constant frequency is 2, 10, 50. So maybe this will be log 2, and this is a log 10, and 50 will be here, log 50. You know that log 2, the log 2 is a pole, the first of the poles. 50 is the second of the poles. This is the first other pole, and this is a first other pole. And no. The 50 is not first. 50 is a twin, is second others. 50 is the second other poles, and log 10 is a 0. So to do that, we need to find out some values. Whereas we define we have a DC gains here. So we define when omega is 1, that is a 14th. So that means here there's 1, and that value will be 14 dBs. And before omega 1, in this area, the slope was, how much is it? Slope was minus 20. So maybe our figure, the meaning is from to here, no, it's like that. That will be minus 20 dB per decade. But it is until we met the pole. When you met the pole, this is the first of the pole, then what happens? There is a decrease. When you met the pole, the slope has decreased 20 more. So there will be change in this manner. In this manner here. There will be minus 40 dB decade. Then we met zeros. What happened to 0? Slope is increasing 20 dB per decade. So in this case, the increase here until we met the poles. There will be minus 20 dB per decade because of the zeros. And we met other poles, but this pole is second of the poles. So in the case of second of the poles, the slope is changes minus 40. So slope is change is in this manner here. Then there will be minus 60 dB per decade. Why? Because of second of the pole change minus 40. In 0, change plus 20. First of the pole, so you can change minus 20. This is the way how to draw the butterfly of the magnitude simply. So you met the zeros, the slope is increased 20 degree. You met the first of the pole, then slope is decreased 20 degree. You met the second of the pole, then slope is changing minus 40 degree. This is a simple way to draw the butterfly. Next, we will discuss about the resonant circuit. So we have assumptions. We have some current source here, and we connect some impedance Z. So So now the impedance, according to the definition of that, the impedance G is V page divided by current page. So this is Vm, set the V, and Im, set the I. So we define that is a Im Vm set the V peg minus set I. This is the impedance. So let the IT is Im cosine omega t, and define this is a Vt, that is a Vm cosine omega t plus theta. So in this case, we have tried to get what is a G. So we have some experience in simple way, like that. In this manner, this is omega radian per second. This Im is current, and Vm is volts, and they have another things. That was the theta. Theta is the load angle here. So when in the same circuit, but when omega is 200, we have test. When in source is 0.002, then the result, the Vm is 6.6, and this is 48 degree. The frequency increase 220 radian per sec. Also, source is the same, but the measure values is increased. And page angle 3, the 2050, even though we have the same source, the voltage is different, and this is a 0. And if we insert 270 radian per sec, frequencies increase. Also, we have the same source, then the result is reduced at this point, minus 21 degree. This is experimental result. So what's the meaning of that? We have one more things. 300, we have the same source, then we measure the voltage, and that was 7.4, and phase angle is minus 43 degrees. Yeah, according to this experimental result, what we can guess? I mean, because this is a simple fixed circuit, then the impedance is a function of omega. So G, when omega is 200, in case 60.6 and 48, that is 6.6 and 48 degree, and source is 0.002, and this is 0 degree. So there will be 3,345 degree. This is ohm. So that is plus Ch13-4. What's the meaning of that? This will be R, and this will be L. I mean, this is a RL series connection. How about the G is frequency is 300. So in these conditions, then there is a 7.84 and minus 43. 7.4 and minus 43 degree, same source in this manner. Then the result was and there is 2706 minus J 2, 5, 2, 3. This is real, this is R, and this is minus values. What's the meaning of that? That is a capacitor. So that means this is a R and C series connection. It means the same circuit, according to the frequency, it looks like RL or it looks like RC. Especially, so in this case, the omega is 250, then there is 10, 0 and 0.0020. So that is 50. Then what's of that? This is just R. I mean, no reactance. I mean, there are nothing in the L or C. Here, we call this frequency, we call this conditions, we call it resonant. We call resonance. In Korean, onjin. And this frequency is resonance frequency. So according to the resonant frequency, when the frequency is lower and larger, is different. The impedance is different. So actually, this circuit, the resonant circuit, has two types. First thing is the series, and second is a parallel, the resonant circuit. Why resonance is happen? Because resonance is why resonance is happen. Because inductor L. Okay, I will use other things. Because L is the impedance is J omega L, and C is 1 over J omega C. That is a minus J 1 over omega C. So we can draw the impedance in the body plots. So we can draw this man here. This is omega, and this is impedance G. This is omega. Then in the viewpoint in that case, because inductor L is in the case of the inductor, this is slope is positive, because there is the magnitude of that is L and omega is positive. So it mean according to the omega, the impedance value is increased. So in the case of inductor, impedance is increased in this manner. This is inductor case. However, the capacitor in this manner here, that is the magnitude of that here is 1 over C and minus 1 over C and 1 over omega here. And what happens? Increasing the omega, that will be reduced. So I mean in the case of the capacitor, impedance is decreased in this manner. This is a capacitor. So if you connect L and C in series, L and C in the series, that is J omega L, and this is minus J over omega C. This is the same thing with J omega L minus J omega C. So it will be J omega L minus omega C in here. That if omega is, I will write here, omega C, omega square LC minus 1. So in this case, at omega is the same with here, then this impedance is 0. But when omega is larger than here, then G is approximately is minus J omega C 1. Oh, I'm sorry, it's long. So it looks like, in this case, this is larger than here, so that will be larger than here. So J omega C omega square LC and C omega here, so J omega L. In this case, it looks like an inductor. Yeah, the low frequency, omega is smaller than here, and G is approximately same with minus minus J omega C1. So this is a capacitor. So in this case, in some frequency, in high frequency, this is inductors, and low frequency, this is a capacitor actually. Then the center point of that, this point, this is a resonant. In other resonant circuit is a parallels. We have a circuit here. This is a series. And we have another is parallel resonant. In this circuit is like that. And capacitor here. So in this case, this is J omega L, this is minus J 1 over omega C. So here, G is J omega C plus J omega L1 in here. So in this case, the same frequency, omega is 1 over 2 LC, then G is infinite. Why? This is a same J omega L, J omega c omega square LC minus 1. So in this frequency, the denominator was a 0, so G is impedance. Omega is smaller than that values. G is approximately minus, no, actually in this case, J omega L. Omega is larger than 1 over root LC, then G is approximately capacitor. So in this case, in the low frequency, this is inductor and this is capacitor. And center frequency is a resonant. This is the reason the resonance is happen. The inductance is a positive minus, and capacitor is minus J impedance values. So because of that, we can get this a resonant. So we can drive the circuit of the resonant here. At first is parallel the resonant, the circuit. In Korean, 병렬 공진회로. So to derive generally, so including the resistors, we have some source, and there are R and L and capacitor. This is the R and L and C. So here the G is 1 over R plus J omega C plus 1 over J omega L. So this can be rewrite here is 1 over R square plus omega C minus 1 over omega L and square, and the phase angle is minus arctangent R omega C minus 1 over omega L. So impedance, and the impedance Z can be 0 at omega is 1 over root LC. So we define resonant frequency omega 0 is 1 over square LC, root LC. The dimension is, the unit is radian per sec. We call this is a resonant frequency, in Korean 공진 주파수. Therefore, omega is the same with omega zeros, then G will be same with R. So if omega is smaller than omega 0 or omega is larger than omega zeros, then because G is in this form here, magnitude over here, that means this is increase. Then G is increase. So if we draw the magnitude of G, this is omega and this is omega 0. Here we can get that this is R values. I mean, this is the magnitude of Z. But based on here, because the denominator is increasing according to the omega, so that impedance is reduced. So it looks like, man, you find, okay, this is a 1 over r square plus omega c minus 1 over omega c square. This is the magnitude of z. Especially we have some values here. This is 0.707 r. Exactly, that is 1 over root 2 r. Then you define this. We define this frequency difference between 2 points. We define this as the bandwidth. In Korean, 대역폭. So this is omega 1 and this is omega 2. So this describes that these things we can rewrite G. So G was 1 over R plus J omega C minus 1 over omega L. Then that will be R 1 plus J omega RC minus R omega L. Then there will be 1 plus J R LC omega LC minus omega LC. One here, there will be R. Then you can rewrite here is R 1 plus J R LC, and define this is omega 0, omega minus omega 0. And rewrite this is R and 1, and define this is a K in 1 plus J cube omega 0 omega minus omega 0 here. K is R and Q is R here, and omega 0 is 1 over C. So this is a resonance frequency. And especially we call Q, we can call this as a quality factors. So this variable show us how fast the impedance is varying according to the frequency. This is a reason to use the quality factor Q. When high Q makes a very fast varying impedance. actually, and we have another terms to describe here is bandwidth. Bandwidth is the frequency range between two frequencies. This is this frequency is especially this is the G will be here. So 1 over root 2 is 0.707. So that means the Z frequency, the magnitude is half of 1 over square 2 G at the resonant frequency. So there will be case of K, because we define the K is the maximum values here. Then bandwidth is defined the frequency difference between omega 2 minus omega 1. Then we can calculate omega 1 and omega 2 directly. How can we do that? I mean, because of that here, this is K1 plus Q square omega 0 omega minus omega 0 square. So that means, and this is the same thing with here, each others. So 1 is Q square omega 0 omega minus omega 0 square. So there will be the values from here, omega square here. So we have solution omega 1 will be minus 2Q omega 0 plus and omega 2 will be plus 2Q omega 0 plus that's it. So we can calculate omega 1 and omega 2 together to make a 0.707 the magnitude of here. So from here we can calculate the bandwidth directly. From here bandwidth is omega 2 minus omega 1, therefore was omega 0 and over Q. So we can do this in the series in the series the series resonance circuit. In Korean is 직렬 직렬공신회로. You might you can get it here. So plus minus. This is R and L and C we get here. R, L, C. Then we have Z is a series connection RLC. So R plus J omega L plus 1 over j omega c. There will be r plus j omega L minus 1 over omega c. So in this case, we can draw the admittance of y. Y is 1 over z. So therefore, there will be 1 r plus j omega L plus j omega c, 1 over j omega c. Then here, then there will be 1 over r and 1 plus j omega L over r plus j omega rc 1. Then to be present here is 1 plus j 1 over r L over c omega 1 of c minus 1 omega here is 1 over r. We can be present. This is a k 1 plus jq omega 0 omega minus omega 0 into manner. So we can write here k will be 1 over r, q will be 1 over r, L over c then omega 0 will be same things. And let's see here. So this is the series Lagrange circuit. In the case of series Lagrange circuit, the admittance is more simple to describe the system, the characteristic here.